I'd like to welcome everybody to the 2019 Bullard Lecture, which this year will be given by Gauthier Hulot. Before I introduce Gauthier, I would like to remind everybody that immediately after this lecture, we will have our GPE section reception and business meeting. I know there were some issues with getting tickets. If you don't have a ticket, come anyway. So we hope to see you there. And at that meeting, I encourage people to come because, of course, at our business meeting there, we recognize our fellows and the Gilbert awardee and also our best student papers from the past year. So with that, we'll get started with the main event here. It's my great pleasure to introduce Gauthier Hulot, who is this year's Bullard Lecturer. Gauthier is currently the Deputy Director of Earth and Space Science at IPGP in Paris. And his research over many years now has mostly involved looking at the Earth's main field, the core field, using data, so observations both of a historical nature and of a paleomagnetic nature to investigate the structure in the field, the flows at the top of the core that give rise to that, and to understanding what in turn gives rise to those flows. And much of his work, in fact, his work has spanned both theoretical developments and statistical analyses, as well as looking at observations and modeling. And more recently, he's turned his focus to thinking, at least for some of the time, thinking about the lithospheric magnetic field, mainly through his involvement in several satellite missions, starting with Ørsted, and more recently as one of the international co-PIs leading the French team for the SWARM mission. In addition to the research that has come out of that, in which he has been involved and led some aspects of, one of the things that is really sort of putting forward much of his new work has actually been the demonstration through that mission of an innovative absolute magnetometer, and he's become very interested in nanosatellites. It currently has funded a project called NanoMagSat, which is really to 6-month phase A study from ESA to investigate the feasibility of these absolute magnetometers for use in ionospheric studies and lithospheric studies. He has given service to the international community, most recently through involvement in SETI, IAGA, IUGG. And today he's going to talk about observing, understanding, and predicting the Earth's magnetic field. Gauthier.
Thank you very much, Kathleen, for this nice introduction, and thank you very much to the section for inviting me to give this talk. It's a great honor. It's a bit impressive, and I must confess that when I wrote my abstract, I decided I would try to make something fairly broad that would cover many aspects, so I came up with this title. And as I moved forward and getting closer to the talk, I realized there was so much to be said that eventually I had to focus on some of the more recent magnetic fields. So I apologize to my colleagues, paleomagnetists and archaeomagnetists. I won't be talking too much about this today. But of course, it's a single magnetic field that we have, so we all share the same field. So what is this field? Just let's start with simple facts. It's a field which basically is everywhere on Earth. It is defined by a strength or intensity, and it has a direction. Usually we don't feel it, but one nice thing is that it's quite easy to detect as soon as one has a needle. And this is a very important fact because it's, so to speak, so easy to actually sense with a needle that we do have a lot of data since very ancient times because this was discovered quite early on. Now, another important aspect about the magnetic field is that there are two ways a magnetic field can be produced in physics, either by a magnet or by electrical currents. One thing I should stress, which is obvious but it is important, is that when you measure a magnetic field, you cannot tell which source has been producing the field. You cannot tell whether it was a magnet or electrical currents. And what you actually see and what drives your needle on Earth is basically anything that may be a magnet or an electrical current at the planetary scale or even the local scale. Usually you want to avoid measuring things you produce yourself. So, indeed, there are many sources, so we all know this, but to a large extent, it's important to have this in mind, because what I'll be focusing later on is basically the main field. The main field, because this is the one that is basically the one dominating all the other sources, and this one is produced within the core, the liquid core. This core is metallics, mainly iron and nickel. And because the Earth is still quite hot, it still is liquid, except for its central part, the inner core, which is the crystallized fraction of the core. And it cools. It goes on cooling, but it's being still hot. The cooling is strong enough to drive convection, and in fact, it's strong enough to drive convection that is capable of producing the magnetic field. So this is basically the geodynamo. One thing I should mention is that this driving is basically a combination of thermal convection, basically the heat going away, and the fact that there are some light elements in the core, and that produces also some release of these light elements at the inner core. Right now, the convection in the core is basically thermochemical with this respect. So the field is being produced within the core, and it escapes the core. It goes basically through the silicate mantle, which is a poor conductor. So to a large extent, as long as we look at field changes that are slow enough, when I say slow, it's basically slower than a couple of months, perhaps a year, this field the mantle is transparent and the field escapes. It reaches the surface, and here we have a secondary source, basically because as soon as we get close enough to the surface, the temperature of the Earth is low enough that rocks can be magnetized. Basically two types of magnetization, either because the rock got a remnant magnetization when it's formed, for instance, lava flows, or even now, once it has this remnant magnetization, which, by the way, is the memory of the ancient field, it may also be partly magnetized by induced magnetization. So we have another source of field here. And finally, the field lines, they go up across the neutral atmosphere, where not much happens, and then reaches the upper part of the atmosphere, which is ionized, and is ionized mainly on the day side, a little bit on the night side, but it also heats every morning and cools every evening, and this motion of an ionized medium within the main field produces another source, currents in the ionosphere. And finally, the field lines escape towards the interplanetary medium, where it meets the solar wind, which basically are charged particles that are blown by the wind, by the sun, and these particles interact with the Earth's magnetic field, producing the magnetosphere, and this interaction is rather complex, but from the magnetic field point of view, it basically amounts to a number of large-scale electrical currents flowing around. So what we see on ground with a needle or any magnetometer is the result of all these sources. Okay, now let me introduce the main field today. Well, I'll try to compute the value for today exactly based on the latest models that we've been producing for the IGRF. And this is how the field looks like. So with a few things that I want to stress that most of you are aware of, but these are the things I'd like to comment on later to try to understand, well, explain what we think is the origin of all these features and how they're going to evolve in the future. So on the left, you can see the field intensity. This is at the Earth's surface. And basically, it's you can see that the high intensity is close to the pole. That's what you would expect for a dipole field. Low intensity close to the equator. But obviously, the structure is more complex than the one you would expect for an axial dipole or even the inclined dipole. That's the radial field, and basically what we see is the field coming out from the Earth on the southern hemisphere, coming in the northern hemisphere. the equator is tilted, and again, we see that there is here fairly low intensity, high intensities close to the poles, but some structure. The key point is that basically, even looking at the large-scale field, it is obvious that the field is dominated by a dipole, but it has a strong non-dipole component. Another thing that I would like to stress is that if we now look at the poles, the dip poles, where the field is basically vertical at the Earth's surface, they are highly asymmetric. The North Pole, North Dip Pole, and South Dip Pole are not at all in opposite, how shall I say, in the same latitudes. The North Pole is actually right now very close to the North Geographic Pole, where the South Pole is quite remote. So that's the picture, general picture. Okay. Now, one thing I should stress is that investigating, looking into the way the field behaves is not only a matter of understanding the Earth or fundamental processes. There are a number of practical issues. These practical issues and practical use of the magnetic field that date back to long ago, as we'll see in a second, but which to some extent are increasing. For instance, the magnetic field is very important for space application, especially Catherine was mentioning nanosatellites. Nanosatellites like very much to have a good knowledge of the magnetic field because they use it for their attitude control and many other applications. In general, for navigation, the magnetic field is still used for giving the orientation. It complements the GPS, which is important for many applications, of course. It's also useful for underground drilling and a number of other applications, in particular radio wave propagation modeling, because these waves in the ionosphere are sensitive to the magnetic field. Another aspect is that the magnetic field is also defining the near-Earth space environment. And I've mentioned earlier this area, the South Atlantic anomaly, where the field is particularly low. And from the point of view of the magnetosphere, this is the region where what is known as the radiation belts are getting closest to the Earth's surface. And therefore, there are quite a number of energetic particles that can reach very low altitude, even underground. Fortunately for us, most of these particles are stopped by the atmosphere. But for satellites and any technology in low Earth orbit, this is a concern and it can, for instance, produce problems with computers, with instruments, and in which case interruptions of services or even loss of instruments. So it is a concern to try to figure out how these things are going to evolve. Okay. So the question I'd like to address in the rest of this lecture, well, I say partly because I cannot cover all aspects, but I wanted to have a story to tell. So I want to start with the data that are available and also remind you of the way these data are actually being collected and used to reconstruct the main field, and of course its recent evolution. Now, I'll next move to explain how progressively we've been able to relate what we see in the main field evolution to what is actually happening within the dynamo in the core. And then the last thing I'd like to talk about is about recent developments, because the field is very active. Well, not the magnetic field. The scientific field of the magnetic field is indeed very active, and there's a lot of progress that is being made. So I'd like to highlight all this. Okay, so brief slide. I won't go to all the detail of this, just as to remind you of the fact that the needle was discovered. It's very important for navigation. People started thinking it was pointing north, everything was fine. Then they realized it was not always north, so they had to map it. Then they realized that the maps were changing, so you had to actually monitor the magnetic field. That somehow is the good news for us, because this is the very reason why people have been collecting a large amount of data, and that we can have access to these data for investigating the past magnetic field. Another important thing I'd like to stress is that the initial measurements were mainly directional measurements, because these were the easiest to make, and it took a while before we actually came up with a solution to measure also the strength of the magnetic field. This solution was generalized by Gauss in 1836, basically. So The full measurement of the magnetic field only truly started in 1836, but we do have information for the field about the field at early epochs. Okay, now one of the nice things about the efforts of Gauss and his colleagues, von Humboldt and Weber, is that because they realized the importance of monitoring the field, they set up observatories, and this tradition has been long-standing and improved and consolidated. And I'd like to take this opportunity to also remind you of all the hard work being made by people who actually acquire the data on a permanent basis. This is hard work, and I think we really need to acknowledge the extreme usefulness of this, not only for now, but for the future as well. So right now, the tradition has been kept and is organized through the Intermagnet network, which is running, actually it's a network which is coordinating the observatories run by more than 60 institutions. And so we have these magnetic observatories currently working, and this is, of course, very important. This is also an opportunity for me to remind you of what the magnetic field looks like if you are within an observatory. The nice thing about an observatory is that you don't move, so the field is, if the field is changing, you actually see the temporal changes. And this is just to highlight the fact that indeed the magnetic field is sensitive to all the sources I mentioned earlier. On the upper panel left, you have the typical daily variation, which is related to the ionospheric sources. So at noon, the signal is the strongest, and then during the night, it becomes much quieter. On some days, the field can be much more agitated, because that's when we get what we call a magnetic storm. That's basically when the solar wind is interacting with the main field more actively than usual. But on the long term, if we wait for having what we usually call quiet days and take averages of all these things, then we can see the long-term evolution of the field, which the order of magnitude of which is about 30,000 nanotesla to 50,000 nanotesla, depending on where you are. So, one important thing, so this is I won't have too many equations, but I think it's really is important to remind us of the fact that we still rely on something that was introduced by Gauss in basically 1840, who, by the way, invented the spherical harmonics just because he wanted to solve this problem. He also introduced least square methods on that occasion. And anyway, the nice thing is that he came up with something absolutely fundamental, because it's good to have measurements, but you need to have a strategy for making your measurements, and you need to collect your measurements into something that makes sense. If you have declination on one hand, inclination on the other hand, how do you collect this into something that is the full picture? So the idea, of course, is that you need to rely on the fact that when we do the measurements at the Earth's surface, we basically have a magnetic field which is in a source-free region. So the field can be written as deriving from a potential which satisfies the Laplace equation. And what Gauss has demonstrated is that the potential can be divided into two terms, one which is reflecting the sources inside the Earth, and one which is reflecting the sources outside the Earth. And now the nice thing is that if you have measurements, by definition, your measurements are related to these red and blue coefficients, which are the unknown, but the parameters that describe the true field. And every time you have a measurement, then you have an estimate of a linear combination of these quantities, so to speak. So if you collect all your data, you next face what we call an inverse problem, and then you can estimate your Gauss coefficients. Once you have this, you can next separate the Gauss coefficients that come from the internal sources, those that come from the external sources, and this is in fact how Gauss demonstrated that the main field was of internal origin. I'm stressing this because this is really still the way we handle the data. We collect all the data and we try to make sense of all these data through the Gauss coefficients, which can next be used to produce maps and look at the way the field behaves. Okay. So one or two things that I'd like to stress. I mentioned earlier that before 1840, there was no intensity data. And of course, this is a bit of a problem, because if you don't have intensity data, you don't know how strong the field was. But there was also a question that actually was raised early on and was made kind of, it became an interesting problem when Mike Proctor and Dave Gubbins realized that if one makes measurements of the direction of the field at the Earth's surface, then in fact there may be situations where different fields might have exactly the same direction at the Earth's surface. And this is a problem because that means that the Gauss coefficients, you cannot actually compute them if you only have these information. And so I just wanted, so this is the counterexample. The two fields here, so this one is at the Earth's surface. So the direction here is basically the same as the direction here, but as we move away, the two directions become very different. If I superposed, perhaps you see this a little better. So this, to some extent, was a bit of a theoretical question, but it was, in principle, it meant that perhaps we could not use the directional data in the same way as we could use the other data before 1840. In practice, most people had noticed that this was not so much a problem, yet there was this counterexample. So we looked into this some time ago, and I just want to say that we're very fortunate because the magnetic field is mainly a dipole field. It only has one north pole, one south pole, and in that case, it turns out that indeed, you can recover the entire geometry, the entire structure of the field just knowing the direction. Of course, you don't know the absolute value of the field, but you can recover everything to within a global factor. And this is very fortunate because it means that we can go back in time. Another interesting question that arose later on, and that was when satellite data became available, and in the same spirit, and you may want to know what happens if I only measure the intensity of the field. If you only measure the intensity of the field, the situation is not quite as nice, and we run into problems. This was something that people realized as soon as they had launched the early satellites, and that George Bacchus actually understood. And, but in that case, we know that we need to have extra information. The key information is the location of the magnetic equator or vector information close to the equator as a general rule. The reason I'm insisting on this is that this is what made space magnetometry slow to actually develop into something fully operational. You really need to make vector measurements. You cannot just make intensity measurements. Okay, so just here a temporary conclusion about ground-based data, because that was also a motivation for going to space magnetometry. We have the observatories, but they are not so well distributed at the Earth's surface. And typically, in the description I mentioned earlier in terms of spherical harmonics, we can go only up to degree 8, which means that we can only see the very large scale of the field. And this is a great limitation if one wants to understand what is going on in the core. What is nice, in contrast, is that we have a lot of data from the ancient times. So the situation is that we can get a picture of the field which is relatively low resolution for the historical time, but with some period of time in the past. And that's the kind of thing that actually Andy Jackson, Dave Gubbins, Jeremy Bloxham had been doing, and this is how we get very nice pictures of the field since basically the 16th century. Okay, now, as I said, this is a limitation. Ground data are too sparse, and they also are on the continents, and this is not very good. So the idea was to move to satellite data. There are great advantages, especially if one is at low Earth orbit, because these orbits are basically of duration of about 90 minutes. That means that on a single day, we can cover basically a lot of the Earth's surface. The problem with satellites is that to handle the data, we need to be very careful. The situation is different from the ground data. Ground data, if anything changes, that's because the field itself has changed. If you are on a satellite, of course the field is changing, but it's a combination of the fact that the satellite is moving from one location to another and the fact that the field itself is changing. So we need to, the ideal situation is to combine the information from ground and the information from satellite. So here I'll go quickly through a little bit of history of space magnetometry, because it's interesting. Actually, the very first scientific measurement ever made in space was the magnetic field. But the data was not very good, and nothing was actually done with it except for just checking that the field was looking what it would be looking as, well, what people expected it to look like. These initiatives were taken by the Russians, and then the American, of course, with the Apollo program, got very interested in monitoring everything in space. And they launched a large suite of satellites, and in particular these OGO 2, 4, and 6 that carried some magnetometers. But this is exactly when they realized that if you only measure the scalar field, you get into the trouble of what is now known the Bacchus Effect, and you cannot recover accurately the field unless you have a way of knowing where the magnetic equator is, or basically having some vector data. So of course, you can combine these satellite data with ground-based data, but the huge advantage of the orbits of the satellites cannot be taken as long as you don't have the vector data. But measuring vector data, vector magnetic field from space is not an easy task from a technological point of view. You need to have a very accurate attitude restitution system. Any slight error in the angle of the direction of the field will translate in errors that will stop you from doing good maps. So it was only in the 80s that the US managed to actually launch the very first truly scientific satellite in the, truly efficient magnetic satellite for magnetic investigation. And, but these were the early times. The satellite was launched on the dawn-dusk orbit because it needed to have sun all the time for the batteries. And of course, one of the problems is that the satellite sees the ionosphere as an inside source. And since it's dawn-dusk, there is a signal. So sorting out the signal from the ionosphere, from the core field, was a bit of a problem. Another thing is that the satellite didn't last very long, but it did last enough that a very nice picture of the main field could finally be done, and including not only the main field, but all the sources of internal origin. And one of the main conclusions was that this was the first time that the limitation imposed by the crustal field was actually seen. One of the problems when we want to witness the core field is that basically the internal field is partly hidden by the magnetized sources within the crust. And here the historical picture here is basically the main field. This is a power spectrum, and here the main field is dominated by a dipole. Then you get the non-dipole terms, and then as you can see, as we reach degree 13, the spectrum becomes flat, and this is the signature of the lithospheric field, the crustal field. And that is a problem, because if you want to investigate the core field, then this is going to stop you from seeing the details of the core field. So we know that we can only see the core field up to degree 13, essentially. Okay. Then a number of other satellites. I'll be a little quicker, just to say that it took another 20 years before actually any other satellite were launched. So the initiatives came from the Danes with Ørsted and the German. There was some delay with Ørsted. So the two of them turned out to more or less be in orbit together. One nice thing about it is that the two satellites had understood that it was important not to stay in the same local time and cover all types of local time to better clean the signals from external origin. But having two satellites made it also possible to understand that if we have several satellites at the same time, then things become much better. So this was sort of the first multi-satellite configuration. And eventually this led, after during the mission, we realized that we had to do something to maintain this space magnetometry, and we moved to Swarm, and this is a constellation where we now have three satellites. These were launched in November 2013. Swarm is 6 years old now, and it is planned that it will last up to 2024, perhaps more, which is nice because it's a full solar cycle. and that would allow an even better understanding of the various external sources, and as a result also a better understanding of, well, a better way of cleaning the magnetic field of the main of the core to better recover the information. Okay, so this being said, let's have a look at the field. We mentioned the South Atlantic anomaly. This is basically a set of pictures taken from the IGRF, 1945, only observatories. Then we had MaxSat, then we had Ørsted and Champ, and recently Swarm. The key point here is that, as you can see, this South Atlantic anomaly keeps on growing. Another thing is that it's deepening as well. That is, the minimum is becoming smaller and smaller. This is a plot that was done for the previous IGRF models. And as you can see, the minimum basically is now close to being on the order of 22,000 nanotesla. And the foci of this minimum is drifting slowly towards the west. Another thing that is interesting to monitor is the evolution of the poles. And of course, the dipole field itself, that is, the geomagnetic poles are opposite to each other. They do not move so much. However, it's interesting to see that the dipole field, which was tilted by about 11 degrees in the past, is moving closer to the pole. And the other thing is the dipoles, and this is highlighting how much non-dipole contributions there are in the field. The dipoles are basically behaving very differently in the north, where basically it started very far from the geographic pole, that moved slowly and then accelerated, and is now currently very close to the geographic pole, less than 4 degrees, while at the same time, the south dipole moved from relatively close to the pole, away from the pole, and still moving away from the pole. So we have very different behavior. This is the speed of the drift, and as you can see, in the case of the North Pole, there was a sudden jump here, acceleration, whereas in the South Pole, the motion was relatively regular. I'm showing this because these are surface manifestations of the field, and the interesting thing is to look into how we could, can we come up with an explanation for these features, and as a result also, is there a possibility of predicting how they will evolve in the future? Another aspect, of course, is the change in the intensity of the dipole field. So the dipole field is progressively declining, so be careful that this is basically the G10, that is the axial dipole, but it is negative. So this increase, in fact, means that the intensity is decreasing. And indeed, and the full dipole is decreasing. Actually, the full dipole is decreasing faster than the axial dipole itself. And since 1900, the full dipole lost about 9% of its magnitude. Okay, now one important thing is that so far we've had the data. I showed you some maps at the Earth's surface, but these coarse coefficients, we can use them to down-continue the field up to, number one, the base of the mantle, because if we assume this field is indeed produced by the core, it means that there are no sources in between the Earth's surface and the core, and the theory of Gauss basically applies, and we can use these Gauss coefficients to infer what the field looks like at the mantle of the base of the mantle. Another important thing is that we know this is also going to be the field at the surface of the core, provided we only focus on the radial component of the field. This is an interesting, there are two things. One is that we can down continue and see what happens at the core surface, which is where the action is taking place. But it's also important to realize that anything we see at the Earth's surface is the consequence of what is happening at the core surface. We don't see what is happening inside the core. We just see what is happening at the surface, and this is driving all the action outside the core. Okay, so this is a movie that I've taken from a paper from Nicolas Gillet in Grenoble with historical data, and this is going to show how the field has been evolving since 150 years, which is since the time we've had the intensity data. I'd like you to see a number of things. One, this is typically the situation, so in 1840. As you can see, the field indeed is mainly dipolar, with the field coming out from the south, going inside the core in the north. But there are plenty of regions where the field lines are actually coming out and back again inside the core. And this is particularly true at the core surface here, where we have a reverse flux here. And this reverse flux is the cause of the South Atlantic anomaly. You will see also these patches moving around, and this is, as I just said, exactly the cause of what we see at the Earth's surface. I will also, I want you to just have a look, and you will see that most of these features are basically moving westward. So this is basically the evolution of the field over the 150 years using historical data and some of the recent satellite data. Okay, now a few things that can be done, and I'll try to be quick on this, is that you can do a number of diagnostics. For instance, you can infer what is the cause in terms of which of these features are responsible for the decrease of the dipole field. And this is relatively straightforward to do, because what matters is the integral of BR multiplied by cos theta. And what happens, and in a recent paper by Metman, I took this picture from there, you can see that the reason basically why the field is decreasing right now at the core surface is because of this reverse flux, which contributes negatively to, well, in that case positively because the dipole is negative, but this is the main cause of the decrease of the dipole. So a number of diagnostics can easily be done by just looking at the way the field behaves at the core surface. Another interesting case, for instance, is something we had done with Arnaud Chidia some time ago, and when we realized that the north dip pole had suddenly jumped, and that's looking at what happens at the core surface in the region where the field is sensitive, or more precisely, corresponding to the field lines that are responsible for the dipole, the dip pole in the northern area. And here what we see is that basically the cause of this is the increase, or in fact the emergence of a new reverse patch in that region that basically is dragging the pole. So again, we can identify the things happening at the core surface that are responsible for what we see at the core surface. Okay, now the next thing is that we want to interpret, and there are several ways we can interpret this. And one way is then to write the equation that is, in fact, driving the evolution of the field at the core surface. And as I said, what we see is the radial component. So the main equation we're interested in is this one. And we know how to write it. And the answer is that if the field is changing, it's because of diffusion and because it is affected by the flow at the core surface. And there has been a lot of effort to try to figure out which of these components are actually driving most of the changes that we see. And I'll be rather quick here because I don't want to spend too much time on this. But it's interesting that these questions are not very easy to answer because we are stuck with the fact that we only see the large scales. We have no access to the radial derivatives. So we need to find some way of assessing which of these components are the most important ones. In addition, there are hidden scales of the main field that can interact with the small scales of the flow, which we anyway don't know, and this is a great limitation. A number of tests have been done to try to assess this, and I won't describe these things. And jump to the conclusion because I'd rather focus on what I want to say after. And basically the consensus is that on average, diffusion does not seem to be required to account for most of the field evolution of what we see. However, I already mentioned this case of the core of the dip pole in the northern hemisphere. And in fact, it's very easy to show that this evolution indeed can be the result of some diffusion that led to the increase of this flux patch in the northern hemisphere. That was recently shown. So there are situations where diffusion obviously is needed, but in general it's not absolutely necessary, and we can try to do some assessment of what is driving the field at the core surface in terms of core flows. So the trouble with these things is that these equations are not fully determining the the flow. So we have the secular variation, we observe the field itself, and this is an equation we can use to invert for the flow. And before the advent of numerical simulation, this was the main way of trying to infer what is happening at the core surface. Because of this non-uniqueness, some extra information had to be introduced, and one of the most successful one was the approximation which was introduced by Lemuel, based on the Navier-Stokes equations, and which basically is stating that because the core is a fast rotator, the Coriolis force is playing a major role, and many of these forces can be neglected to the extent that we have an extra constraint here. Now, these type of flows can next be used, the constraint to infer the type of flow. And here, this picture I wanted to show mainly because this was the first time that we had high-resolution images of the secular variation. That was just after Maxet and Ørsted. And these led to the first images of how the core flows would look like, with some considerations about the type of vortices that could be seen. There'll be much more interesting results after, so I'll skip this, but this was important because it really kicked off the calculation of core flows at high resolution using magnetic data. An important thing is that also one way of testing whether the core flows calculated had any chance of being realistic was something that was proposed by Dominique Jot some time ago, because these flows, if we are correct in inferring them, some of them should carry the angular momentum of the core. And if this is the angular momentum of the core, this should correspond to what is missing in the length of day if we look at the momentum of the mantle. And these led to a number of calculations, and the nice thing is that it indeed led to some very consistent results, even though there were a number of issues. But this was a strong demonstration that the core flows calculated in that way had some meaning. Okay, now more recent work about this, and I'll try to be quick on this, but this is important, is if we look at the way the field is changing, the secular variation, then what happens is that the secular variation can vary slowly itself, but from time to time there is a jump and the trend is changing. These things have been termed geomagnetic jerks. They had been discovered in the late 70s. But in the recent years, using the satellite data, we realized that there were more and more of these type of events, and it is interesting to actually see what the satellite data tell us about these jerks, which usually come in pair and form what is now known as pulse acceleration at the core surface. So this with satellite data, and this is a movie I've taken from Chris Finley, and it's showing now the acceleration. And as you can see, indeed, at the core surface, we do see a number of pulses that happened close to the equator and which are responsible for the changes that are seen at the Earth surface. That's again the same strategy. We observe something, we do the map, we see what happens at the core surface. And in fact, when we, well, not me, but when these, in that case, Metman and Finley and his team looked into the possibility of explaining these jerks and pulses, they actually showed that indeed these could again be explained in terms of core motions at the Earth's surface. Now, the interesting thing is that while this was developing, then 3D numerical dynamo simulation was also developing. And I took this picture of Edward Bullard. I found this one interesting because this is basically what a computer looked like when he published his 1954 paper about homogeneous dynamos and terrestrial magnetism. And I don't know if at the time he was thinking that perhaps someday it would be possible to compute 3D numerical simulations. But since that time, a lot of progress has been made, in particular since the end of the 90s, and a lot of calculation could be done. Now, I I'm afraid I won't have time to get into all the details of this, but one thing that is important that I want to stress is that numerical simulation relies on the full dynamo equations. There are a number of them. You can recognize again the secular variation, the induction equation here. And some of these simulations, there have been a lot of them, and they are driven by a number of non-dimensional numbers that are important to bear in mind. And the main message here is that there's a lot of simulation that has been done, and but many of them have share a number of properties, but there are a wide variety of simulations as well. Anyway, the key point is that there are a number of parameters that are important, some of which are really difficult to match with what we expect for the Earth. But so if I want to make a short story here, what is nice eventually is that all these simulations have a number of parameters that are important to assess to look into the core and try to figure out some explanation for what we actually see in the real data. So, for instance, the Ekman number is not correct, the magnetic point number is not correct, the point number is not correct. However, in terms of the Alsacer number, which basically is predicting the magnitude of the field, we can get dynamos that in general have magnitudes that are quite consistent with what we see. Another important parameter is the magnetic Reynolds number here, which is a measure of the importance of these two terms with respect to each other. And these dynamos tend to produce terms that have similar ratios as what we would expect for the Earth. So the key point here is that these dynamos, they generally are doing not too bad at explaining what we need to explain at the Earth's surface. Okay, then we have a lot of those dynamos, and one of the things that Uli Christensen started looking into when he was visited IPGP was that trying to sort all of them and trying to figure out which of these dynamos were actually those that were looking most Earth-like. Because if we want to make progress and see try to explain what we see at the core surface and try to see if we can predict the evolution, we need something, some dynamos that are Earth-like. So basically, we define 4 parameters, put all this together, and then Uli came up with an area, well, a region in the parameter space, where here we have the Ekman divided by the magnetic point number, the Reynolds magnetic number, magnetic Reynolds number here, and basically anything in here looks very much like the Earth. And this has driven all the efforts to produce most of the dynamo simulations that people are actually using now. This is an example for this red triangle of what the simulation is looking like. Okay, so these criteria allow you to have some big picture, some dynamos that look at a given instant and statistically like that of the Earth. There are other things that are important to do, however, is that you also want these dynamos to evolve with timescales that are comparable to that of the Earth if you want to be able to predict the field or at least reproduce some of its behavior. And here the dynamos turn out to be very nice to us. And if we look at the time scales defined as the rate at which basically how much time it takes for a given scale of the field to change in a significant manner, this can be formalized in this way, then both the Earth's magnetic field and all the dynamos happen to share a common law, and this allows to define what we now define as the secular variation timescale that allows all the dynamos to be rescaled in such a way that they evolve in time much like the Earth. So the nice thing about this is that looking into all these dynamos, we can look also for some boundary conditions that make them even more Earth-like, and that's the type of efforts that Julien Aubert has been doing within IPGP. And here, this is what I'm showing here, one of the main dynamos that he came up with, where by coming up with boundary conditions that reflect what is imposed by the mantle and some consideration about the way the mantle and the inner core are connected to each other, then he managed to produce a field that not only is behaving statistically in an Earth-like way as defined by Uli, but also in terms of the time scale as defined as just described before, but also it reproduces the fact that the field is mainly active in the Atlantic Ocean, and there is a general drift of the field. So it contains the basic features that we need to explain what is seen in the case of the Earth. So here, just this dynamo simulation actually is, for instance, capable of reproducing things that are very much similar to the pulses that I had been describing and are responsible for the jerks. With similar timescales, the movie is a little longer, so it changes a little faster, but we have something very similar. And in fact, we can next, and that's the big advantage of numerical simulation, look into the detail of what is happening inside. And if we do this, then in that case, what these authors came up with is that the cause of the jerk, in fact, is indeed related to azimuthal acceleration linked to buoyancy and these waves. This is the equatorial view. These produce waves that propagate up to the equator, where they concentrate and produce what we saw. So these dynamos, they're fully capable of reproducing a number of features that we see. Now, the next thing that can be done, and I'll try to make sure that I can finish my talk in a decent time, is there are two avenues that people are trying to use now by taking advantage of the numerical simulation. One is that since we have simulation for which we know what the values are for the flow, for the diffusion, some statistical information can be derived that can next be used to make much better inverse calculation of the flow. And this is an example that I've taken from a recent paper by Nicolas Gillet, and which basically shows some of the structures. These are the North Pole, so there is this giant gyre that basically flows around and gets close to the tangent cylinder here, with one feature that had been highly advertised in the recent years, and that is that this flow here is kind of accelerating. The other thing is that with this better approach, using the statistical information and for the inverse problem, we no longer have to rely on the tangential geostrophy or whatever approximation. We really can rely on something which is much closer to what the dynamos are actually showing. And this is, again, the length of day prediction, which have been much improved. Okay. And then, of course, the next thing is that we can also look at how the dynamo looks inside if we teach the dynamo what it should look like. That is, if we use data assimilation approach, in that case, what is usually called sequential data assimilation approach, then what happens is that using the data, the core flow can be recovered at the core surface, of course, but much information can also be inferred about the state inside, and we can, to put it simply, teach the dynamo what it should look like to actually reproduce what is observed. And if you can do this, there's a nice consequence, and this consequence is basically that you can next let the dynamo evolve once it's properly scaled. It has been told what the field was at a given instant. I'm making data assimilation very simple here, but the idea is that you can next let the dynamo evolve and see how far it can go in terms of predicting the field. And indeed, this is something you can do, and so we did this with Julien for the purpose of a paper that we had published with some colleagues who were interested in the evolution of the South Atlantic anomaly for the basically radiation belt evolution. And these basically are my last slides, but to illustrate what can be done with such data assimilation and prediction of the field using these new tools. So here, the nice thing, of course, is that for data assimilation and prediction, you can run several simulations, allowing for errors, uncertainties, and the information that you have. And this is important because, of course, as the uncertainties will grow, and this is an illustration of how far you can predict the field. So on the left, this is basically one solution which is closest to the ensemble behavior, so that's our best guess of what will happen. And then on this side, it's another model which basically is illustrating how things can depart. So have a look here at the evolution of the South Atlantic anomaly, where at the core surface, so you can see that it will move towards the west, and then in the end, we get basically structures that indeed look quite similar but starts diverging. In fact, it turns out that in a study we had done some years ago, we know that with that type of dynamo simulation and using data assimilation, then we shouldn't expect to be able to basically go much beyond 50 years or something like that, very much in the same way weather prediction is limited because of nonlinear effects. So that's what we see at the core surface, and if we go back to the Earth surface, this is how the South Atlantic anomaly looks like, its evolution. So that's what we've seen already. That's the situation in 2015. It's basically the same for the two models. Here I have highlighted some ISO values. So here this is 30,000. The external one is here 26,000. And as we move forward, you will see that the prediction is that this anomaly is going to grow. And again, the minimum intensity is going to decrease further in the next, up to 2050. And this is clearly, we're going to reach the 22,000 nanotesla. But as you can see, depending on the simulation, there are some slight differences. Of course, one thing I didn't mention is that you can test the ability of these type of simulation at predicting the future by doing some hindcasting exercise, but I didn't have time to look at and explain this aspect. What really matters is that the message I want you to keep in mind is that we can now basically hope to be able to predict beyond the standard 5 years that people have been using when doing, for instance, IGF models. Another prediction of the model is the pole motion. You remember the North Dip Pole had been accelerating and crossing, getting close to the North Geographic Pole. And actually what happens now is that the prediction says, yes, it will go on moving, but it will decelerate and it will cross towards Siberia. In the meantime, the South Dip Pole will go on moving, but slowly, slightly further away from the South Geographic Pole. Decrease of the magnetic field. This is an illustration where here I've plotted several of the solutions just to illustrate the divergence of the solutions, but the decrease is predicted to go on for some time further. Now again, beyond that, can we predict how far we can go? Using these dynamos, it is unlikely that we really can do and say anything about this. And here, that's a quick slide about a question we almost always get when we give these talks is, are we going to have a reversal? So from the perspective of these simulations and the predictability of the field, it is quite unlikely that we would be able to predict anything in this respect. And in that case, for instance, this is a simulation where a slight perturbation led a prediction that was to reverse to decide not to reverse. So with this type of methods, there's nothing we can say about the future of the next reversal. Of course, this does not mean that nothing can be said about reversals, but then you need to think in a very different way, more like you would think of climate with respect to weather. And if you're interested in this, I suggest you have a look at the paper we recently did with Matthias Morsfeld. Okay, so I'm finally finishing my talk. I apologize, I miscalibrated my slides. But anyway, so some concluding comments and a few words about challenges. Now, I think I've convinced you of the huge progress that has been made in our ability to model, understand, predict the magnetic field since the time of Bullard. So it's not only the time of Bullard. The key point is that we not only have observations, we now know where the observation come from, what is happening at the core surface, what are the phenomena that happen within the core surface, within the core, and we can also now connect dynamo simulations with the observation. And I think that this is really a very nice development with some significant success. And the important thing too is that it opens the way for making prediction possible. And a lot of efforts are going into this right now. It's a very active field. There are a number of challenges, of course. As I mentioned, numerical simulation can reproduce fast behavior, pulses, jerks, etc. But right now, they're not completely included in the data simulation scheme. So we still have the issue of predicting jerks. At this point, the simulations are not yet capable of predicting this. There's more work to be done in that direction. But we already saw that we have dynamos that display phenomena that are very much closely related. From the observational challenge, that's something that Catherine mentioned earlier, it is very important that we go on monitoring the field from space because we only have 20 years of good space data, and the phenomena we're looking at are basically on that scale. So we really need to have more data and also improve the space and temporal resolution. We've had swarm, and this demonstrates the usefulness of constellations. And now we have new ways of doing things, and I'll finish with this. There's this NanoMaxSat project, which basically is trying to go on doing a constellation much cheaper so we can have this on a permanent basis. But there's another aspect that I also want to highlight, and a lot of effort have been put into this, is that there are plenty of magnetometers in space for a variety of reasons, and these magnetometers can also be used. They cannot be used alone, but they can provide very useful complementary data, and this is the type of things that Niels Olsen at DTU has been looking into. And this, I think, will provide even more data, and more progress is in front of us, I'm pretty sure. I apologize for being a little long, but I hope you enjoyed. Thank you very much.
Thank you very much, Gauthier. We're over already, but if somebody has a burning question that they would like to ask, please come forward to the mic. Put your hand up so I can see where you are and make your way over. Okay, I'm going to ask one question and take chair's prerogative then. In terms of the nanosatellites, what do you think is the most important question that they can address sort of first, you know, in the relatively near future in terms of field observations?
Well, I think that the main point is that having nanosatellite will allow to deploy a constellation that covers the local times much faster. That's the key point. So the hope is to reach smaller scales of the core field and faster time scales. And incidentally, one thing I didn't mention, which is also a critical issue, is that we will have to start to worry about the mental conductivity and the way the signals are distorted. This is something that some people already thought about, but for the time being, we kind of leave behind the carpet.
Great. Thank you very much. I'm going to now present you with the certificate for your lecture. So this is from AGU. Thank you very much.
Thank you, Catherine.